All right, welcome back, everybody. We are moving into 6.3, and we're going to talk about ocean currents in these guided notes. Now, 6.3 is a little bit longer, so we're splitting this in half. So this is 6.3a. All right, some key vocab. Ocean current, Coriolis effect, rip current, and upwelling. All right, the major ocean currents. So an ocean current is a large volume of water flowing in a certain direction. Wind-driven currents are called surface currents because that's where the wind hits. It hits at the surface. Surface currents carry warm or cold water horizontally across the ocean surface. That means horizontally is left-right, not up and down. Surface currents can extend to about 400 meters below the surface. That's about 4 football fields. And they move as fast as 100 kilometers per day. That's about 60 miles per day. The Earth's major wind belts, called prevailing winds, influence the formation of ocean currents and the direction they move. So it's caused by which direction those winds are going. Now, there's something called a rip current. A rip current is a narrow, powerful surface current which flows away from the shore. It's caused by pressure building up from uneven buildup of water from waves. They can flow very quickly and can be difficult to detect until you're in one. And again, it goes away from the shore. Rip currents are responsible for about 150 deaths every year in the United States. About 80% of all beach rescues are related to rip currents. Rip currents don't pull swimmers under, they flow out for several miles. So they are moving from the shore out into the deeper water, so it pulls the swimmer outwards into the ocean. If you get caught in one, swim parallel to the shore. So swim, like you're swimming along the shoreline until you are out of the rip current, because they aren't typically going to cover a lot of area. So once you get past it, you can then swim back in. Now, the Coriolis effect is the movement of wind and water to the right or left that is caused by the fact that the Earth is spinning. We are rotating, so it is causing some things to move. It causes fluids such as air and water to curve to the right in the northern hemisphere in a clockwise direction, and it causes fluids to curve to the left in the southern hemisphere in a counterclockwise direction. You can see that on the image. It kind of gets deflected in clockwise, so around like a clock to the right, and then to the left on the bottom. The shapes of continents and other land masses affect the flow and speed of currents. So the continents themselves, these big land masses, kind of get in the way. Currents form small or large loops and move at different speeds depending upon the land masses that they are contacting. Upwelling is the vertical movement of water towards the ocean surface. So vertical is up and down. Upwelling occurs when wind blows across the ocean surface and pushes water away from an area. Deeper, colder water rises to replace it. So as water gets skimmed off the surface, cold water from below has to come up. And it often occurs along a coastline, as you can see in that picture. The wind is coming from the coast towards the ocean, pushing the water away into the deeper ocean. And that is causing that upwelling, or that cool water, to come up near the beach. It brings cold, nutrient-rich water from deep in the ocean to the surface. Density currents are a type of vertical current that carries water from the surface to deeper parts of the ocean. And we learned about density in the last section, where we talked about how cold water will be more dense and it would tend to sink, and warm water would be less dense and tend to float. So these currents are caused by changes in density rather than the wind. So that's caused by that kind of more dense water sinking. Density currents circulate thermal energy, nutrients, and gases. So that's how you can transfer colder water down, warmer water comes up. Now, impacts of weather and climate. Warm water currents and cold water currents affect weather and climate in different ways. Regions near warm water currents are often warmer and wetter than regions near cold water currents. So here you can see that in the North Pacific, where the blue arrows are kind of hitting the northwest United States, like around Washington, that's going to be cooler. So they're going to be a little colder, have some cold water currents. It's going to be a little cooler in those areas. Whereas as you keep going around, it starts to warm back up again, and as it goes towards like Hawaii, it would be warm. The Gulf Stream is a warm water current that affects coastal areas of the southeastern United States by transferring lots of thermal energy and moisture to the surrounding area, or to the surrounding air. That is an area where you get a lot of hurricanes moving up through the Gulf Stream, moving across the islands up towards Florida and along the East Coast or into the Gulf of Mexico. Now, that is a warm water current that comes up there and brings with it a lot of energy. The cold California current affects coastal areas of the southwestern United States. Typically, you don't see as many hurricanes out in the Pacific, on the Pacific West. You just don't have the energy. The Great Ocean Conveyor Belt. That is the name for a model of the large system of ocean currents that affects weather and climate by circulating thermal energy around the Earth. So it's circulating that temperature, that heat around the Earth. In this model, high salinity water cools and sinks in the North Atlantic, and deep water returns to the surface in the Indian and Pacific Oceans through upwelling. So it's a huge cycle, a very large cycle, where that high salinity water cools and sinks. It's more dense. And then that deep water returns in a very different area. And here you can kind of see it. Scientists estimate that the Great Ocean Conveyor Belt takes about 1,000 years to complete one cycle. So you can see the high salinity water cools and sinks in the North Atlantic, and it's hard to kind of picture that, but that's pointing towards the North Atlantic Ocean. And then you go down around Africa, and that deep water returns to the surface way over in the Indian and Pacific Oceans. So it's a 1,000-year cycle.
It's a digital writing assistant that you can download as a browser extension.
So here's a short little video.
Extremely helpful.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis Effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds on to heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow, or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them. What about the creatures that adapted to survive in these swirling seas? Take a closer look at some truly fascinating...
So that is where we will leave off with ocean currents. So things that you want to take away with you are the vocab from the beginning, so the Coriolis Effect, the Great Conveyor Belt, and how water moves around the planet in currents, and both vertical and horizontal currents.